and we will. So the problem statement is a bit flip of a number x is chosen a bit in the binary representation of x and flipping it from either 0 to 1 or 1 to 0. For example, x is equal to 7, the binary representation is 111 and we may choose any bit including any leading zeros which are not shown and flip it. So in this binary, the representation, we are having the representation as 111. So if you consider the MSB bits, those will be 0. So we can flip the first bit from right side to get 110. That is, if you flip the LSB, we are going to get as 110. Now, if you flip the second bit, only the second bit, then we are going to get the data as 101. Suppose if you are considering the leading zeros, and if you flip the fifth bit from the right, so 1, 2, 3, 4, 5. So then if you flip this particular bit, then we are going to get the data as 10, 111, etc. So given two integer, which are start and goal, return the minimum number of bit flips to convert the number which are given in the start to goal. Now we will see the example. First, we are given with a start is equivalent to 10 and the goal is equivalent to 7. And the output here it is 3. We will see how we will get this output. The binary representation of 10 and 7 are 1, 0, 1, 0 for 10. For 7, it is 0, 1, 1, 1 respectively. We can convert the given start data, which is 10, to the goal data, which is 7, in 3 steps. Now, if you observe the bit pattern, we need to flip the first bit. So, whenever you flip the first bit of the source data, so then we are going to get the data as previously we have the 10 is equivalent to 1010. We require to flip as the destination is consist of 1. So, when you flip this data, what is the output we are going to get is 1011. This is the first flip is required. Now, if you say the second data, as these two bits are 1, so here flip is not required. Now we go for the third bit checking. So when the third bit, if you observe, the input is 0 and the goal is consist of 1. So this bit we want to flip. So when you flip this particular bit, we are going to get the data as 1111. Next, we have to examine the fourth bit. If you observe the fourth bit are 1 and 0 in start and goal. So we have to flip this data. So when you flip this data, we are going to get the data as bit pattern 0, 1, 1, 1. If you observe the binary representation, this one is same as that of 7. So it can be shown we cannot convert the start number 10 to 7 in less than 3 steps. So minimum 3 flips are required. So hence we are going to return 3. Now we will see the second example. In the second example, the start is equivalent to 3, goal is equivalent to 4. Now we have to perform conversion from start to goal. The output is 3. We will see with the explanation. The binary representation of 3 and 4 are 0, 1, 1. For 4, the representation is 1, 0, 0 respectively. So here we have to convert the start number, which is 3, into the goal number 4 in 3 steps. Now we will see how we can convert. So taking the source number, which is equivalent to 0, 1, 1. If you observe the bit 0, here the bit 0 of the start and goal are different. So we require a flip. So when we flip the LSB bit, we are going to get the output as 0, 1, 0. Next, we will examine the second bit. If you observe the start and goal data, here the bits are complement to each other. So here also we require flip. So this data will be considered for the second bit. So we have to flip the second beta. When you flip the second bit, then we are going to get the data as 0, 0, 0. Now we have to examine the third bit. As this third bit also complement to each other, we require a flip. So now we will take the 0, 0, 0. We are concentrated for bit 2. Now bit 2 is going to be flipped. that we are going to get as 100, which is the binary equivalent of 4. It can be shown we can't convert 3 to 4 in less than 3 steps. So hence we are going to return 3. Now, so in the first example, the start data is 10 and the goal data is 7. So for 10, we are going to write the binary representation. Similarly, for goal, we are going to represent in the binary format. 10 we can write as 1010. 7 we can write as 111 for the same number of bits. So 0 will be placed in the leading 0, that is MSB. Now we will examine one bit. We will see whether the flip is required or not. Now, if you observe the LSB bit, so in this LSB bit, the source and the goal, these two are of different bit format. So here we require a flip. If you examine the bit 1, so in this bit 1, as the source bit in B1 position and the goal bit in B1 position, as these two are of same, so here flip is not required. If you examine the bit to bit, the source data that is start will consist of 0, whereas goal is equivalent to 1. As these two are complement to each other, we require a flip here. Now, if you examine the bit 3 position of the start and goal, these bits are complement to each other. So here also we require a flip operation. So in total, we require 1, 2, 3 flips. So we are going to return 3 as output. If you observe the bit pattern in the source, that is, which is a start number, if you observe the start bit and the goal bit in a particular position, BI, if BI is equivalent to 0 in the start as well as in the goal, here the flip is not required. If BI bit is the start bit is equivalent to 0 and the goal bit is 1, here the flip is required. Similarly, if BI bit in the start, if it is 1 and in the goal, if it is equivalent to 0, in this case also we require a flip. Whenever the BI bit in start and goal, if these two are 1 and 1, then the flip is not required. If you observe this truth table, whenever the two bits are 0, 0, here the flip is not required. That we will consider as 0, 0, 1. Flip is required. That will consider as 1, 1, 0. Here flip is required. This will take as 1, 1, 1. Flip is not required. That I'll write as 0. If you carefully observe this two table representation, this logic is analogous to XOR operation. Now we go for doing the start data and goal data. We will XOR. Once we XOR, so what is this XOR will give? So whenever we XOR the data which is between the start and goal. So if the start data is XORed with goal data, whatever the output we are going to get, in that if you count number of ones in the data, number of ones in the num, that is nothing but the XOR of start and goal that I am assigning to num. So if the number of ones in this num, if you count, that will nothing but our output. So we had to fetch how many number of ones are there after XORing the start and goal. Now we will see. Now we will see the logic for this or algorithm kind of thing. So what are the various steps we have to consider is we had to perform the XOR between the start number and the goal number. So this we will take with some number. So num is equivalent to start we had to XOR with goal. This is the first step. Once we got this number, we have to count the number of ones in the data which is num. After counting the number of ones, so return count. So these are the steps which we have to follow for finding out the number of that is flips are required for converting the start number to goal number. So same example again we will take. So here the start number is 10. The binary representation is 1010. The goal number is 7. 7 binary equivalent with the 4 bits representation is 011. Now we have to perform the XOR operation, that is num is equivalent to the start XORed with goal. So when you start XOR with goal, what is the output we are going to get is 0 XORed with 1, 1, 1 XORed with 1, which is going to result as 0, 0 XORed with 1, which is going to result 1, 1 XORed with 0, which is going to result 1. So now this is the number which we got after XORing the start data and goal data. So in this, if we are able to identify how many number of ones are there. So here we have a 1. In this bit position we have 1. In this bit position we have 1. If we count the occurrence of 1, that is nothing but the output. So in this example, the 3 positions we are having in 1. So this we are going to replace. So it is a straightforward step where we can do the XOR operation between start and goal. And now the logic we have to find is how we can convert, or whatever the number which we got, how we can count the number of one presence in the number. If you have some data, let us consider 1011. Some random number I'm taking which is equivalent to 11. Our objective is we have to find how many number of ones are there in this particular data. So some logic we have to apply so that it has to count the number of ones are present in the data. One way is the first logic we will say, this I'll take as method 1. We'll take the number where the number we are taking as 1011. In the step 1, we are going to add with 1. So when you add this one with 1, we are going to get the data as 1 and with 1 is 1. And the remaining bits, we are going to lead the bits with 0, 1 and with 0, 0, 0 and with 0, 0, 1 and with 0, which is resulting 0. As the result is equivalent to 1, we go for incrementing the count, which is count is equivalent to count plus 1. Now, initially, we will initialize the count is equivalent to 0. Now, the count is going to be 1. So, once the step is done, in the second step, we are going to shift this data by right time towards right side by 1 bit. Now the number is going to be, which is nothing but 1011 shifted towards right side by 1 bit. When you shift this one towards right side by 1 bit, we are going to get the data as 101. Now you go for ANDing with 1. So 1 we can write as 001. Now you go for ANDing this bit by bit. 1 is AND with 1, 1. 0 and with 0, 0, 1 and with 0, 0. So as the result is equivalent to 1, here also we are going to be increment the count. So that will write as count is equivalent to 1. The previous count is 1. Now if we increment by 1, we are going to get the count is equivalent to 2. In the next step, again this number, so in the step 3, we will take this number as shifted towards the right side by 1 bit. So when you shift the data towards right side by 1 bit, we are going to get the number as 10, and we are going to AND this one with a 01. So when you AND with the 1, so 0 AND with 1 is resulting 0, 1 AND with 0 it is resulting 0. As the result is equal to 0, so we know need to be change this count. So count will be still retaining 0. In the next step, so that is in step 4, the previous data. So in the step 3, we have the number is equal to 10. So now this number will be shifted towards right side by 1 bit. When you shift this number towards right side by 1 bit, we are going to get the data as 1. We are going to be AND this one with 1. So 1 AND with 1 is resulting as 1. So as the result is equal to 1, so we are going to be increment the count is equal to count plus 1. So the previous count, so till the step 3, the count is 2. When you increment this count, 2 plus 1, which is going to be result is 3. Now, if you go for fifth step, again, what is the step we have to perform is 1, we have to shift towards right side by 1 bit. When you shift this data here, number will not of the iteration. Now go for return the count which are present. So here we are going to return the data as 3. Now we will see the code for this. So now we have to write a function which is for minimum bit flips. The input is start, output is goal, and the return type is integer. So for count, we have to declare one variable. So that we will write as a variable identifier. I'll take as CNT. We will initialize this one with a 0. Next, the number. We will find the number by XORing the start with the goal. So that we will write as start XOR with goal. Next, the stopping criteria is until this number is greater than 0, we have to iterate the loop. So what is the logic we have performed is, so whatever the number which we are having, this number we are ANDed with 1. If the result is equal to 1, we are going to be increment the count. So that we will write as CNT plus is equal to 1. So this loop will be iterated until the n number is greater than 0. For once each and every step is done, we are going to check the number is ANDed with 1. If the result is equal to 1, increment the count. After that, for the next iteration, so the number will be converted as the num is equal to the given number is shifted towards right side by 1 bit. So once this entire loop is done, we are having the result is in count. So we go for return that particular count. So that will write as CNT. Now we will see the method 2. In this method 2, first we'll take the number where the number is equal to start XOR with goal. Whatever the number is obtaining after XORing, let us assume the data is 10 XOR with 7, which is going to be result as 13. That is what our number. Same logic we will apply like when our number is equal to greater than 0, we will do the AND operation between the number and num minus 1. Whatever the result we obtain, that we are going to be assigned to num. Here we no need to check any condition. Every iteration, whenever num is greater than 0, we are going to perform num is ANDed with the num minus 1. Then we are going to be increment the count. So count is equal to count plus 1. So the logic for num and num greater than num minus 1, it will use to update or it is going to clear whatever the bit pattern we are having, bit 0, bit 1, bit 2, bit 3. If you have k number of bits, whenever you perform the num ending with num minus 1, so it will clear the first occurrence of 1 from LSB. Whenever we do num ANDing with num minus 1, so it will clear the first occurrence of 1 from LSB. So in this, now we are considering the number is equivalent to 30. In the binary format, it is equivalent to 1101. So the logic we are having is num, we have to AND with num minus 1. So here the num we are going to be considered as 30. And the binary equivalent is 1101. Num minus 1, that is 13 minus 1, which is equivalent to 12. 12, the binary representation is 1100. Now we have to perform AND between this 1 and with 0, 0, 0 and with 0, 0, 1 and with 1, 1, 1 and with 1, 1. So if you observe the number and the result whichever it is obtained, what is the difference you can see? The LSB bit is cleared, that is B0 bit is cleared here. The next occurrence of 1, once the LSB bit is cleared, next we are going to see B2 bit. So now what is the current number we are having? So the number is updated with num and with 1, which is current state. The num is equivalent to 12. In the binary format, this we can write as 110. We are going to add with num minus 1. So the num minus 1 is nothing but 12 minus 1, which is resulting 11. So the 11 0 1 1. Now we go for ANDing this data. 0 and with 1 0, 0 and with 1 0, 1 and with 0 0, 1 and with 1 1. So now if you observe the number and the result, the bit 2 is clear. So after performing this operation, bit 2 is clear. For the next iteration, the number is equal to, after ANDing num with num minus 1, whatever the result is obtained, that is nothing but number. 1000 is nothing but 8. So binary equivalent we are writing as 100. We are going to AND with num minus 1, where num minus 1 is 8 minus 1, 7. 7 binary equivalent is 0, 1, 1, 1. Perform the AND operation between these two data. 0 and with 1, 0, 0 and with 1, 0, 0 and with 1, 0, 1 and with 0, 0. So as the result is 0, that is number is equal to 0, this is what our stopping criteria. Now we go for stopping the iteration. Now if you observe the number and the result is obtained, here bit 3 is clear. So total how many steps we have considered is, this we can take as step 1, this is step 2, this is step 3. So this while loop we have iterated for 3 times. So for every iteration the count will be incremented by 1. So initially we will take the count is equal to 0. This is the first step. We go for incrementing the count, that is 0 plus 1, which is equal to 1. For the next step, C is equal to 1 plus 1, which is resulting 2. This is the third step. So count is equal to 2 plus 1, 3. So this will pass as out. Here we are not checking any condition. Just we will do num and with num minus 1. What is the advantage with respect to this is, if I have a 32-bit number representation, out of this 32-bit, only one bit is 1 and the rest of the 31 bits are 0. So how many comparisons or how many steps we are going to take place is always 1. If it is a normal procedure as method 1, it has to be iterated for 32 number of times. So this will reduce the time required for execution. Now we'll see the code for this logic. So for implementation of this logic, we will see what are the steps which we have carried out. So in the first step, the num is assigned with the XOR of the started data with the goal. In the second step, we have done num is assigned with num ANDed with num minus 1. For this particular step, the count is incremented. So count plus is equal to 1. Then we have done a condition like if num is greater than 0, go to step 2 else. So what is else means? This else is nothing but if num is equivalent to 0, return the count. Now we'll see the program for finding out minimum bit flips. The function, it is taking two inputs, one is start and the one is goal. The return is integer type. So first we will initialize the count, that is identifier C and I am taking for count, which is initialized to 0. Then we will form the number where the number is equivalent to, it is XOR of the start with the goal. So we will form number is equal to start XOR with goal. We will check a condition where num is greater than 0. Then we will assign num is equal to num and with num minus 1. For each and every step, the count will be incremented by 1. So CNT plus is equal to 1. Once the loop is iterated, then we are going to return the count. Thank you. So in this session, we have discussed the minimum bits which we require to flip so that the given the start number we can convert into goal. Thank you.